Okay. So the live stream is going. Get the backup Zoom recording going. Okay, so welcome to the fourth and final night of the 2021 Altaz workshop. I've been thinking of tonight as Big Scope Night. As you can see from the agenda, the smallest scope that'll be mentioned tonight will be a 30-incher. So I think that qualifies as a Big Scope Night. We're going to start off with the 800 millimeter project, which I think everyone will find very interesting. Michele Scotti is going to walk us through the project he and three others have been working on. We'll follow that up with Tong Lui talking about his 40-inch 3.3 folded Newtonian. Mel will give a second presentation on all of the big glass and telescopes he's working on. And we'll end up with Dan Gray giving us an update on the 36-inch telescope he walked us through on the design phase last year. So with that introduction, I'll turn it over to Michele. Am I saying it right, or did I forget how to say it?
Perfect.
Oh,
perfect.
Okay, very good. Close enough.
Spot on. Let me see if I can share. Do you see my presentation?
Yes.
Let's see if it works in presentation mode as well.
Yeah, looks good.
Excellent. Okay. So my name is Michele. I'm really honored to be able to present this 800 millimeter telescope project tonight. Let's get started right away with the team, a team of four. Charlie is our senior master glass pusher. Then we have Marco and Paolo that are basically doing the heavy lifting, and myself. Charlie is actually pivotal in all this endeavor because he's the guy that you see in this picture. I think he ground kind of 100 mirrors in his life, and he went up to 500 millimeter of aperture. He actually had 3 telescopes. Now he owns only one, and he has always thought about the next step. So going something more than 500 toward 1 meter aperture, right? So it's always fault. And as soon as we got into the conceptual phase, we said the mount is our Achilles heel. As a matter of fact, the one that you see in the picture, his personal scope, is struggling to track for more than 10-15 seconds. So we say we need to get on a different league here. So where to start? Where to get the blank? How to model in CAD resources, fundings, and I'd say that a good place to start is with being clear with the intention of this project. So the mission that we stated for this project is to build a proof of concept, so a kind of prototype, attainable or DIY friendly platform or imaging system capable of doing science, and to be then shared as an open source. This is to close a gap that we identified. Is on the left is what you can see as a representation of, let's say, a pinnacle of amateur astronomy. You see a lot of talented people that are taking amazing picture, and usually they go up to 16 inches, 400 millimeter. And then on the other side, you have the pros. You have observatory class telescope, meters and above. And there's a kind of a gap in the middle. So what if we are building a telescope to validate a sizable imaging platform? What if we then provide all the drawing, CAD models, and the process description what if we take away the second guessing, and so people can rely on a validated prototype? My vision is that of a success is that a bunch of guys in Australia, a university in India, a capable amateur astronomer in Germany can do their own version. They can tweak the design as they want, but on a validated platform. That is the intent of this specific project. And what you can do with that, to me, is with a robotized large telescope, you can collect a lot of scientific data that you can give back to the scientific community. Sure, you can take nice picture. Of course, you can use it for public open nights, a lot of different stuff. But to me, it's more like you can actually. What if we can tap into maybe 1% of the amateur community and start collecting scientific data out of that for nova, comets, exoplanet, transit, spectroscopy. You know probably way better than me. So how to do that? We lay down the technical feature of this project, and 8 of these. Like the mirror is an 800 millimeter mirror of 31 inches with a focal length of around between 2.5 3 meters. Is kind of flexible. The project itself. It is an Altaz mount. To me is the obvious choice. It has to have a fairly sophisticated tracking system. So that means a drive that is based on SciTech2, plus encoders. For these, needs to be transportable, or that kind of transportable you want to build and leave it in a place and forget about that. A 4 inches focuser, because we say, why not? Let's make it big. And since it's an Altaz, we want to make it as an imager. It needs to have a rotator and a guider included that are combined in a single piece with the focuser. All right. So let's have a little bit of disclaimer, so to speak. What this project it is absolutely not. So it is not the best, meaning that this is not a unique recipe. It is a lot of different ways to do that. And by the way, I would do things in a different way if I had to start from the beginning, different technical solution and stuff like that. It is not a professional tool. It doesn't want to compete with commercially available solutions that are out there already. This is not a plug and play so with a team that is setting it up, and you can forget about that. It is an amateur system, so it needs a lot of care, probably also running it. And third point is not cheap. It is affordable. We want that to be attainable. There are some data that I will show at the later stage, later in the slides. It's labor intensive, even though it's for free in the amateur world. But there are parts that are actually not absolutely cheap. But we're trying to find a way to make it as affordable as possible. So let's get back to the project, or actually what I think are actually 2 different projects in one because of different expertise involved and different timelines somehow. So it is, you see on the left, the mount with his own challenges, and on the right, the mirror. So there are also 2 different parts of the team that are taking care of the 2 different things. But they two both integrate holistically, because if one of the 2 fails to meet the specification, the whole thing doesn't really work completely. So let's have a look at the dimension of this telescope, just to have a taste of what is this. Starting from the bottom is the azimuth table is 1.2 meter wide, so fairly fairly robust foundation. And as of now, in this configuration, that is the one the picture is, I think, is a 3.75. It is slightly higher than 3 meters in total. So you will need 3 or 4 step ladder to have a look at that. But in my mind, it's like I really want to have my mom being able to look at the eyepiece if she wants, and not being too scared to fall from heights. The what I call project ethos here are the guidelines that we want to stay with us while we are taking decision on design of this project. So when I say no frills means that everything needs to be there for a reason. When we are taking decision on the design, it doesn't need to be something that doesn't need to be there because we like it, or because it looks good, or because we have always done that way. It doesn't need to be a reason to be for a feature to be there and done in a certain way. And we can tap on some modern tool like FEA, or there's a lot of stuff that you can utilize to have your decision driven by science and by data. So kind of form that is following function at a certain extent. And of course, it needs to be DIY friendly. I keep highlighting that and underlining that because it needs to be a key aspect of the project. So let's now have a look at a little bit of some of the actual parts, because so far it's like a lot of CAD models and so on. Is this actually real, or there's something going on? And these are just random picture of parts that we have manufactured so far. I'd say starting from the top left, you can see a 27-point mirror cell with it's not fully completed. You see the wiffle tree on the bottom. Then going in the central part, you see the hexagonal upper telescope assembly is almost pretty much finished. Under that, you see the azimuth table, and you can probably guess on this 1.2 meter platform, you see a rail, a stainless steel rail that is part of the azimuth bearing. On the right, you see a snapshot of the system that is actually the focuser, the guider, and the rotator all together. Below that, you can see the dry run of the assembly for the lower telescope assembly is pretty much done. And the legs at the very bottom, the legs of I call it the tripod, is the legs on which the azimuth table is sitting on. And you might guess that at the end of this leg, you see bearings. There's bearings assembly, so that the entire table is rotating onto that. There are 4 different areas that I hold dear in this project that I think are key for the success and the completion of this project. In processes that are elementary, even though complicated. There's a little bit of a contrast here, is that, but it's giving me a chance to spend a few words on the fact that I really wanted to have in my mind process that are giving the chance to anybody around the world to go to something like a Home Depot, getting material that is ready available, and utilizing that in a smart way, and be able to build something that is accomplishing the target here. On the right, you see the structure with an holistic view. So effectively, we spent a year and a half, if not more, just on the CAD, and then routinely going through the analysis with the FEA and other stuff like that, just to make sure that we're starting with a design that really stand a chance to do what we want that to do. Encoder, snooping on plane wave. This is really was like definitely a good advice from the community here. Is like an encoding system that can be reliable and then can do the job here based on a ratio system in this case. And the mirror that is a project by its own, you will see at a later stage. I have 3 slides here on processes that are, to me, key for this project, meaning that are key for success in light also to be able to be implemented anywhere in the world. So this is, for example, is the azimuth table on the top, and it's like sandwich. Like, so how do I take poor materials and make it something that is robust and light at the same time and affordable? So here you have like maritime grade plywood, and they sandwiched and glued together with that kind of foam that is that insulation material that you find on your ceiling usually, and then you can get in this configuration you can turn fairly poor material into something that performs very well. On the bottom is just few picture of the process involving the what I call the Pac-Man, is like the trunnions. So this is a sandwich as well. And on top of that, because when we were thinking about the design, we really need to think things in advance. You see that there are cutouts in the foam where we put some insert of wooden insert, so that when you have an anchoring point or when you have bolts and so on that are going through that, we really don't want to go through foam, but something more robust. Second process here, a little bit tricky and with a funny description. So we don't have a CNC. We don't want this project to be close to any CNC shop and so on. So we go from computerized numerical control to actually human analog control. So let me explain here a little bit. What you see in this picture is my attempt to build a grinding machine, a rudimental grinding machine on the Pac-Man, so on the workpiece itself. In this specific case is to grind the rails on the perimeter of the trunnions, so that when the entire telescope swivel on two ground bars, that is a fairly common design in this kind of telescope. You actually have a fairly precise surface, and you're going to make the life of the guiding system, or the auto guiding system, much easier. So here the attempt is really to reproduce a kind of a huge bearing, but within, I wouldn't say microns, but with a tolerance that is making the life of the bearings the life of the auto-guided very easy. Next process is bonding, a new way of joining things. And again, I don't want to be close to a weld shop, because a guy in the Philippines, a guy in Argentina, a guy in wherever you want in the world, you might not have access to a nice welder. And in this case, you're maybe welding 1.5 millimeter thick aluminum that, I don't know, that translates in inches, something very thin. So to keep also the cost and the weight very as low as possible. And if you use epoxy in a specific way, as we're talking about aluminum here, you can build structures that are very light and at a cost that is minimal, and without the need to go to a shop that is able to weld, and in this case professionally welding very thin walls. Structure. This is something very tricky and interesting at the same time. I could spend hours and hours to talk about this, but I'm kind of proud to say that the design is validated through FEA, finite analysis. The main parameter is that the structure needs to be light and rigid at the same time. There are kind of two things that are in contrast. In engineering, usually, if you want to have something that is robust, you add material, but then it's adding weight, and then the performances of a structure like a telescope that degrade very rapidly. There are a lot of studies on white books for the VLT and other huge project. The FEA is usually an integral part of the design process here. Of course, what you see is wobbling is an exaggeration of one of the natural frequency of the telescope. Is absolutely a key element for the design. On the right, instead you see a deflection analysis. So with the payload or the cameras and filter wheels and whatever you're putting on the eyepiece at different angles, what is the deflection of the telescope? It is within an acceptable tolerance. And on the bottom right, you see a stress analysis. Very interesting if you want to lightweight your design. So that color map is telling you the material that is not doing anything, is not contributing to the stiffness or the robustness of your structure. You can easily cut it out and save some weight here and there. Encoders, this is really, really key for the tracking ability. It's a little bit the oxymoron here is that encoding and attainable are usually something that I always find out being in contrast. If you go to any show and you try to buy a system that is capable to do that, so with at least 10, 12 million ticks per revolution, it is something that is going to cost you, so going to set you off a couple of grand at least, probably 3. You can get something like that in an amateur way somehow. And in this case, my route was buying a couple of encoders from a scrapyard in the Philippines for a total of 150 pounds. And buying a reel of the optical tape. This, I think, is coming from a surplus warehouse in the US for probably $300. And I tested that with an oscilloscope that I bought as a kit from eBay, 20 bucks. Sold it all together, and I was able with that to check that the encoder coming from the Philippines and the optical tape that it was coming from the US, they were working together. Finally, see the tutso signal there. That is working on my table. The next step is to make it work as a system integrated in the telescope. But again, this is absolutely key, and it is basically very similar specification to the plane wave design, thanks to Dan. Mirror, that is the heart of the telescope, of course, is on a side project is given to our senior member of the team. It is an iterative side project as well. We started with a fairly thin piece of glass because the guy really wanted to jump on that and doing something. They couldn't stand still, but it is an evolving thing. So I think we're going through different steps here. I've ordered from Andre and I received a meniscus. So that is a little bit where I would like to go for the full completion of the telescope. But what I'm putting together here are some features that I think are making all of these affordable and viable to a certain extent. So silvering is a big thing to me. It's really like a game changer for this kind of diameter. A fast design here is like it's a bracket because the project is scalable, so you can actually scale it a little bit down to 500 millimeter or 20 inches. You can go up to probably 40, 45. inches, and just the design itself, when it's proven at 800 millimeter, I think is gonna work as well. And meniscus is because I think is the new path for large builds, and I think Mel is gonna give us some update at a later stage. One of the last few slides here is that where we are at. I have a bill of material with a progress bar for each and every of the components, and I don't like to throw estimation how long it's going to take to complete and so on. So I'm going to use something objective and mathematical. So that bill of material with a progression bar is telling me that we are overall at 81.2%. So there's stuff that we still need to do, but most of the components and so on are completed. And kind of amazing, because I don't really look at that very often, but the total bill right now, clearly excluding time, is less than 3,000 euros. I think all in all, adding also the cost for a couple of iterations for the mirror, I think we're going to stay within 5,000 or 6,000 euros. I think I'll be interested to see where we are landing with that, which I think is a fairly good proposition in the end. Next step is once we're building the telescope is to validate that, meaning that I have a FE analysis that I base the design on, and I have means to check the structure and see if the model frequencies of the actual structure that we build are correlating to that, and it's going to be a key aspect of the final stages of the build. I have in mind to simplify the design. There are a few things that can be done in a simpler way, I think, and probably in a even in a cheaper way. For example, the encoder system that are now on the marketplace, a fairly good alternative to the Banich encoder. And we need to find a home. So the idea is to validate that in the place where we are building this project that is in Italy, but in a absolutely horrific place to do astronomy, because there's a lot of haze, a lot of fog even. So we're going to validate the project there, this telescope there, and then we're going to find a place probably up in the Alps or in the Apennines, some place maybe run by another astronomy club that they can take care of the telescope and making it run it. And because anyway, this is going to be fully remotized. Fourth and last point, but actually something that I really hold dear is to make everything open source. Is a little bit a personal thing, because I learned so much from the astronomer community in all these years that I've been into this hobby or passion. So what I like to do is to document processes in terms of the description, fine-tune the CAD, generate all the drawings, and provide everything as an open source, so that again these guys from all over the world, if they want to get into this endeavor, they can have a reliable source of information, and they can tweak the design to their own needs and do exactly what they want. Last slide is a thank you. That is not just your standard slide of thank you, is really thanks to most of the guy in connected to this call and in this community. Really gave me a lot of inspiration. There are countless hours that I spent looking at pictures from various websites, trying to figure out what is the nice design or put in place design solution that were adopted on various amateur build. I was really like the list of people that I would have to thank in person is actually too long. But to me, it's like this project is, I'd say that it's not a novelty at all. There's nothing really completely absurdly new. It's more like putting together a lot of different elements that are, I think, are not mature to condensate into a platform capable of imaging, and that can do something for the scientific community as well. And that's all from my side.
Thank you so much. Very, very impressive. I'm really, aside from all of the technical points, what I'm impressed by is your dedication to making this open source. So anyone around the world can duplicate to some degree your success. This is a fabulous project. And I'm really glad that you were able to present it to us here tonight.
Thank you for your attention. And again, what I was saying is that we might fail. This is like something very new for us, but we put a lot of energy. We kind of push a little bit the envelope, and it might be an inspiration for something smarter than us to pick up this kind of project and take it to completion. So I think it's good to give it back to the community and say, look, do whatever you want with that, and if I can help with some consultancy. Let's put it this way. Otherwise, it's really up to grab for everybody.
So at the very beginning, you talked about the 3 other people on this project, and that it's all Charlie's fault. So yeah, so Charlie is your optician, and
yes.
And so he's the one who's making the 800 millimeter mirrors, and he's making 2 of them. Is that right?
Well, the first one actually is done. It clearly was like a pathfinder, because we started with I think a 1-inch thick piece of glass. So it was really to take the rust away from the grinding machine and getting on with some work, because the guys were so excited and they really wanted to do something. But in the meantime, I ordered a meniscus from Andre from Canada. I actually received it this summertime, but I really need to complete the telescope mount first, so that we can first test the first optic that we have, and then we're gonna go on with the meniscus.
Okay, so I have a question from Mel in the chat. He asked if you can describe the team. How close together do you live? How often do you meet?
Nice question. So we are all from the same small hometown in Lombardy, northern Italy. That, by the way, only if you're fond of violin makers, because it's the hometown for Stradivarius, or Strads, as you say in the US. Unfortunately, I've been living in the UK for the last 7.5 years. So effectively, we try to, with the modern tools of communication, we try to stay in touch, do small pieces of work, and then when I go back, because it's a 2 hours flight from here, from UK to Italy, we usually carve out some time to progress substantially the project. Clearly, me being abroad is not helping, and but that's okay. We're not in a hurry. We're gonna get there, and it's just a matter of time.
Okay, so we have another question. This one from Dan. He wants to know, how will you mount the motors, and will there be gear reducers or belts?
Oh,
friction drive?
Yeah. I for some reason I left it out, but so that's an interesting thing. So I'm leveraging the fact that there's a friction gearing somehow. So the Pacman, for example, is a 1.2 meter friction drive to the ground bars. So that offers already 60-to-1 ratio that is friction drive, that is totally against backlash, because that to me is like the concept here is to keep backlash, that is our foe, as at bay as much as possible. I have sourced and refurbished a couple of harmonic drives. I think they are 100-to-1. And there will be probably a final step, that is the one closer to the motors, that is a 2-to-1 with belt and pullays, probably with a tensioner. And I'm taking off the gearbox from the Pitman motors, because that is a cascade of few gears, and there's a lot of backlash in that gearbox. So I'm taking it, I'm throwing it out. I'm just keeping the motor, and then there's a 2-to-1, 100-to-1, and a 60-to-1 that should be okay for this kind of application, and virtually backlash free or something like that.
Yeah, you should do really well with the harmonic drive reducers. I use those on my 28-inch. And they work perfectly.
Good to know. I studied some technical specification. They are known to have a little bit of a periodic error, but is really fairly tiny, the one that I have, and they are anyway before a 60-to-1 final ratio. So I've calculated that should be totally negligible to the overall performance.
Okay. Very good. Anyone else out there? Okay. Dan looks like he wants to say something. I'm not sure. Oh, he's talking to somebody else. Okay, so never mind, Dan. Thank you very much, Michele. Really inspiring. And again, thank you for being part of our program tonight.
Yeah, thank you for your attention.
Very welcome, very welcome. So next up is Tong. He's going to talk about his 40-inch of 3.3 folded Newtonian. And he is here, but his video and his audio are turned off. He may not realize we're ready for him.
Oh, hi, Howard, is it for me?
Oh, there you are.
Oh, okay, it's my turn, okay.
It's your turn. Yeah, we're a little ahead.
I'll start sharing my screen, right? Okay.
Okay.
Okay, can you see it?
Yes.
Okay, started.
It looks good.
First, I start. Thank you, Dan and Howard, for organizing this great event again, and thank Ross for starting this movement many years ago. So we have learned a great deal over the years and benefited greatly, on many of our products. And this is the 40-inch, just one of the latest, and it's offspring from this LTS movement. So then actually, I have introduced this project. This is probably the third time I'm talking about this one, and it's finally going to be completed by the end of the year. So I'm going to just. I hope this is just a quick update, because this is just some difference, just update from the last year's presentation. And so you can see the design changed a little bit, and the drive system has been changed greatly, but the optical design just remain the same. It's okay. This is just from the last year's. We don't have to get into detail. So what's the benefit of the folded Newton? Because it's just lower the eyepiece, and also make the secondary to be a round mirror, and relatively, and it's a slower mirror. And when you have the same height of the eyepiece. So this is just from the last years. This is also from last year. This is from Mel's, the calculator. I noticed Mel has a new version of the telescope design calculator. It's very nice. And people, if you want to get into that, it's a very nice, a lot of pictures, a lot of detail designs, and very helpful. So you can see here the eyepiece from to the ground is about to the mirror is about 70 inch. Okay, so only you need one steps when the scope pointing to the 40 degree above the ground, and that's pretty reasonable. They only have 3 or 4 steps at the zenith. When scope pointing to the zenith. Okay, the brief summary, the 12-inch mirror is about 7 kilo. The 40-inch primary is 86 kilo. The total weight of the scope is 345 kilo. It's pretty heavy. The reason is we want to make the scope to be robust and so it can be used for both visual and imaging. The eyepiece height is about 98 inch when pointing to zenith. And its scope is go-to only. And we limit to the go-to only so we can have the drive system relatively easier and simple. And we will touch that later. Why we go this way? Okay, scope will be completed by the end of the year. And actually, we have implemented the most of design idea in a 24-inch scope. So it's and thank you, and we get a great benefit from Howard's explanation on his drive system. So we borrowed a lot of ideas from Howard's scope. And also I discussed with Ross and Bruce on many aspects of the scopes over the years. And so it provided a lot of suggestions, great ideas. So scope is truly the offspring of the LTS movement. You can see the blue, the big blue, it's the encoder, the high resolution encoder, on both axes. The primary mirror is finished. And so here the Ronchi and the focal. So you can see there the central part is not that smooth, but that part is not used. So we don't bother to just call it off, call it down. You can see the center is a small hill, but it's not used. So we are not bothered. So it's a mirror is packed and shipped to the customer already. The second mirror is also finished. Actually, it was finished earlier last year. So as you can see, the very straight band from Intergraph. It's pretty happy with the quality of the secondary mirror too. And here the secondary baffle, the design I borrowed a lot. I learned from Dan's scope. And also there's another telescope, the Reynolds, that has some baffle for the focuser. So I also borrowed that idea. Okay, here's our design. So we have the main surrounding baffle. That's it's above the upper cage. Also, the center vertical baffle is the same as the Banich scope, and we also have focuser baffle. And also there is a round obstruction ahead of the in front of the secondary mirror. So there are the 4 parts of the baffle system. And also you can see we have 6 spider wings, and that idea is borrowed from the large telescope book. So Okay, here the view of the secondary mirror. It's a sandwich mirror, and it's 9-point support. And okay, here's the front view, and it's 27-point support for the primary mirror. Okay, this is a lateral support for the mirror. Okay, this is a design Howard's 28-inch drive system. This is Howard's the Atmos drive system, and this is Bruce's design for 20-inch for our scope, and his version 1 drive system is a friction drive, and later he revised it to version 2, which is okay, here is a version 2 drive system with a timing belt. The reason is the scope slips quite a bit, so it changed to the it doesn't have the, so it doesn't want to balance the scope so often, so tediously. So he changed to the timing belt for both the azimuth and altitude, with good result. But there is some problem with the timing belt, but not his problem. For his application, the timing belt works very well. Okay, here's the detail portion, the detail of the Bruce design. Okay, here's our design. So it's we simplify the scope design, so we get rid of clutch. So the scope will go to only. So that will simplify the design considerably. So the motor will drive the shaft directly with a couple. So it's so you can see it's extremely simple design for both axes. And initially we thought we can use a motor drive the shaft directly, and I'm not sure what's we had some difficulties and Dan logged into my system a couple of times, and I'm not sure so we can eventually resolve the problem. But I shipped the motor to Dan, so Dan probably later can give an update on what is going on with it. And now we switch back the plan B. So the motor will be the planetary geared motor, and it's a relatively low backlash. And since we have the large reduction ratio for final stage, there's still about a 60/1 reduction. So it's a backlash is really not that much a big deal. I hope, at least I hope it's not such a big deal. And also for the tracking, the most time the scope is moving just one direction. So it's the small backlash shouldn't be such a big problem. And here's the progress production. So you can see the bearing and the ground board has been completed, and an upper ring also completed already, and the mirror box is completed, and we have a lot of small parts are already completed, and also it's not pictured, and so it's pretty comfortable. It's on the schedule to be done in about 2 months, and by the end of the year. And also the future work. So we want to maybe we can try the drive system with the harmonic gear like the one used by Howard. And all continue the direction, so the direct friction drive. And also ROG and the user installed high resolution encoder system, which is actually already done. And also field the rotator is also actually it's done already. and also we are pretty comfortable. It's a imager capable scope at this point already. If it is finished by the end of the year, so it should be. We'll see how good it for the imaging. So it's here the left part is the rotator, the bottom part is the encoder, and the right part is the encoder with the focuser and the about 3 kilo load, and it runs pretty well. It's pretty robust and smooth. With Stan's help me get the motor tuned and to high resolution encoder, but not that high, and at least it works. So that is pretty much done. It's pretty short, and so I'm done, Howard.
Okay, thank you, Tong. The first question that comes to my mind is that this is your second 40-inch, isn't it? Because you had one that you finished and installed somewhere in Australia a year or two ago. Is that right?
That is, the scope was made. We made a mirror. The scope was made by SDM, by another the local telescope maker.
Okay.
Yeah.
Okay.
Yeah, we made a lot. Actually this mirror is our number 7 1-meter mirror, and we made about 10 already, but this is a number 7 and the 1-meter mirror for this.
Okay.
Yeah.
Okay, 7. That's really impressive. Maybe you could tell us a little bit about how easy or difficult it is to make 1-meter mirrors.
I think that the mirrors, we have the sandwich, we have 2 layers, so it's a much stronger than the single layer. So so we have a much easier time because we make it as a regular mirror instead of, so the mirror at the bottom is not at the top. So we make it as so yeah.
Okay, so you don't have any trouble with with figuring or trying to get away from astigmatism. You're able to figure pretty straightforward.
It's the same problem we have with the smaller mirror. It's harsher and it's harder. Of course, you always have it's more difficult with a larger mirror. But however, this it's just it's not like the mirror that the Mel have. It's not. This is not a revolutionary approach. So this is a evolution from our other mirror. So we don't have that much difficulty.
Okay.
Yeah.
Yeah, and have they all been faster than F4?
Well, this is a F3.3. This is a fastest mirror for the 1 meter. We made this is second 3.3. And this is number 7, but we made a number 10 already because the other mirror are F5. They're much faster and easier to make. And so it's very difficult at 3.3. I will not go faster than 3.3 for the 1 meter, and with at least for our mirror, the sandwich design. It's pretty tough, and also I get it very thin, the glass, and it's going to be very, very difficult if we go faster.
Okay, all right. Dan wrote in another question. He wants to know if your trusses are made out of aluminum or carbon fiber.
The first one is aluminum. The main truss is a 50 millimeter aluminum, and because the customer it's a visual customer, and there's no reason to go beyond that. It should be better with the carbon, and but the first scope, both the upper stage and the middle and the lower part are both aluminum.
Mm-hmm.
And for the lower, the main truss, we use the rod end, just like one with like the plane wave truss tube. So we want to put you can see the truss tube is in the aligned and behind the bearing. It does not interfere with the bearing.
Okay.
Yeah.
All right. Okay, another question. This one from Ed. He's asking if you have any issues with print through from the separators and the sandwich mirrors.
No, we don't have any print through, and because the reason is it's we have pretty thin thick glasses for the 1 meter mirror. It's a 25 millimeter glasses, and each layer, both layers are 25 millimeter. So it's thick enough to and also we approach it pretty slow. So it's not a fast, very fast the polishing.
Yeah.
And yeah.
Okay.
Absolutely. You can see from the image we have that there's no print through, and you can I think we can.
Yeah, your Ranchigram and your knife edge
Yeah.
there. Yeah.
So at least at this level, you don't see a print through
Mm-hmm.
at this detail, and it could be on a microscope, but it's not at at this level.
Yeah. No, I can see that. Yeah, there's certainly nothing there to worry about.
Yeah, no, you can see a visually. There's a center hill, central hill, but it doesn't bother us, and we don't use that portion.
No,
Also, yeah, and
the secondary will cover that.
Yeah, it's not very smooth at the center portion, but they are largely behind the 12-inch secondary mirror. So it's,
Okay.
it doesn't bother us. It wasn't pretty. It's not pretty, but it's about okay.
Yeah. Okay, and Dan has another question. How did you make the access encoders? Did you use a standard Renishaw incremental encoder?
I bought it from
you.
You know everything. You know the parts number I used. Okay.
Okay. Okay, so you got it all from Dan.
Yeah, it's a 100. Yeah, I bought the encoder from Dan, and it's a Renishaw encoder. It's 100 millimeter ring. It's a 15 million ticks per revolution, and it runs very good. You can. I hope I have. Actually, this is online. You see the blue, the lighting, and on the so the encoder is running in this picture. So it's very strong signal, and it's runs very well.
Okay.
Initially, I thought it has some issues. If I turn the encoder with my hand, I miss a lot of ticks. And finally, I realized although I run it, I turn it slowly, but it's very jerky by hand. So it doesn't, it shouldn't count. And it runs very well. Yeah.
Okay.
And also, it's very easy to install on the scope because it's a very robust encoder. And for the Atmos, the encoder runs as a hub for the telescope. So it's it's very easy, very robust, and it's a rock, and it's portable. So you don't have that.
Okay. That reminds me of a question I had. Is your customer for this scope going to put it in an observatory, or is it going to be transportable?
I think this is a transportable. The reason they bought us is the pick us is because we are transportable scope.
Mm-hmm.
And it's also at a higher resolution. It's imaging capable, and they want it to be a portable scope, and also with the high resolution, so they can track and make image at a very crazy requirement, and with guiding. They want a sub-arc second tracking accuracy. So we have to, but under fast speed guiding. So the only thing we as long as the scope is robust and the mount is accurate, and we provide enough tick, and all on there. So it's their job to make sure it actually guides. And
Okay, that's really impressive. Okay, and Jerry has a question that I think I can answer. He wants to know, is the back of the mirror flat or curved to match the front? And if this is anything like your other mirrors, the back is flat, the back plate is flat, and the front plate is a meniscus.
That is true.
Yeah.
So,
Okay.
so this is why we can make it, as a regular mirror. And so when there's no special way, so we want to make sure that's the same way we make other mirror.
Okay, very good. Let me check to see if we have any more questions. No. Okay. So, anybody else out there have a question? If not, let's take a 5-minute break.
Okay, thank you so much. Thank you everybody for all the questions.
Thank you, Tong.
Okay,
And
thank you,
great.
Howard.
I can't wait to see the finished telescope.
Okay, yeah, sure. I'll probably take some video and sure, at least give another update next year.
Oh yeah, absolutely.
Okay.
Yeah, you're already on the program.
Okay.
Okay.
Sure. Okay, thank you so much.
Thank you. All right.
Okay.
So, okay, take a 5-minute break.
Okay.
And Tong, if you could stop your screen
Sure.
sharing.
Let me see how can I do it. I figure out. Okay.
Okay. Okay, I'll stop your screen sharing for you.
Where the oh,
Yeah,
you got it already, right? I stopped it already,
yeah,
right?
I got it.
Okay.
Okay, so 4 minutes, everyone. Take a short break. We're really ahead of schedule so far. But I think we'll make up for that with the next 2 presentations. Okay, back in
So Howard, can you see my full presentation?
Yeah, it looks
Okay.
good. Yeah, you're all set. Let's do a time check. Yeah, let's go about another 30 seconds or so, and then we'll get it going.
It's strange when I cut from 2 screens to 1 with just the laptop, PowerPoint and Zoom are not happy with each other.
I noticed that last night myself, yes.
They used to be, so I don't
Yeah.
know what's happened.
No,
But,
it has been updated recently, so.
One trick I've learned with PowerPoint and Zoom is make your adjustments to PowerPoint, do whatever you want to do with it before you share your screen, and then share after you've made your adjustments. And that seems to work better.
Okay. All right, let's make a note of that. All right, so let's go ahead and get started here for the second half of tonight. Mel is talk is titled "Another Round: Bend but Don't Break and Some New Ideas in Telescope Making," ending with prospects for a 1.07 thin meniscus and a backseat 0.5 meter scope. So with that, take it away, Mel.
All right. Well, thanks, Howard. And this is Mel. Hello to everyone. This is my second presentation. This is my hardware, bend but don't break. All right. Interesting. Okay. So, retrospective, making the twin 30-inch f2.7 thin meniscus mirrors. The problem is not the thinness, it's not the meniscus shape, it's not the glass type, it's not the number of support points. All those are gremlins that either are imaginary or can be easily dispersed with. The biggest problem with large thin menisci is supporting the mirror's edge. Additionally, parabolizing these beasts is quite the challenge. In fact, wrestling with the parabolizing gremlin, I've actually had to alter my process to where I use pads to pre-polish and then I just start right in with parabolizing with a pitch. The reason is that invariably I end up making 2 passes to get it right. Interestingly, the second time is 1/4 to 1/10 the time it takes to do the first failed attempt, which tells me the first failed attempt is all about learning what's going on. So let's take on one of these gremlins here. Here's parabolization. Normalized for an 8-inch f7 down there in the lower left-hand corner. And you can see that the first 3 or 4 mirrors or so have a lot of parabolization. They aren't too difficult, really. It's just like thinking of a 20 or 24-inch mirror, all that parabolization being squeezed down into a smaller mirror. But then when you get up to the 25 and 30 there on the far right, that really is another world. The projection then is when
Excuse me, Mel.
Yeah.
Is the scale on the left-hand side the number of waves of parabolization?
It is.
Okay. All right. Excuse me. Go ahead.
So you can see then the projection on the 42 inches that the parabolization is even more out of this world. All right, well, let's go and tackle this edge gremlin. This is from R.N. Wilson's book. He looks at mirror support systems for 4-meter mirrors. And he looks at the analysis for several of these. So let's just go through these. The first one there on the far upper left is a Swishinger support where the mirror is held up at the top and supported from underneath. I'll show you a picture of how that actually works here in a moment. The second one is a mercury bag that completely surrounds the mirror. The third one is if it just surrounds the bottom half of the mirror. And by the way, amateurs have attempted this by putting water into inner tubes and holding mirrors that way. The bottom left one is our favorite or sling from the devil, depending on how you feel about it. There in the bottom middle is one of my favorites, which is just 2 points at 45-degree separation for vertical or 90-degree separation from each other. And then that last one is a single point support. And I'm going to talk about that single point for a very interesting reason here. If you look at the graph, you'll see that the belt and the V support is not that bad. I mean, nothing compares to the ideal support, but compared to the other possibilities, it's not too bad. And there in last place, lagging along, is the bottom edge support. So what is this Schlesinger edge support? So here's my drawing, my conception of this. This is inspired by a beautiful Brazilian 20-inch that was featured in Sky and Telescope so many years ago. Around the mirror's rim at the center of gravity, and Arjen Wilson is careful to say that these supports need to be at the center of gravity. They degrade quickly when they are not. These tabs are glued to the mirror. Then hooked to each tab is a bar on a pivot with a counterweight at the other end. So you can see, if you look at the ones near the top of the mirror, that those are holding the mirror's edge up. And if you look at the ones at the bottom, you'll see that those are pushing up, compressing the mirror's edge at the bottom. The ones there on the side are contributing the cosine, the influence that they're supposed to have. So here we have, again, on the left, those systems, and on the right are analyses of 4-meter deformations. And you'll see on the Schlesinger support that it's really good. The mercury bag that's completely surrounds the mirror is pretty good too. And the sling there on the lower left is not so bad either. There's a little bit of triangular deformation in there, typically lost in the noise of the diffraction pattern, but that depends. And we're going to talk a bit about this one on the lower right. You notice there near the bottom, but not right at the bottom, is the point of maximum deformation. Right around it, to the left and right, it's really bad. At the top of the mirror, it's also bad, but not quite as much. And then you notice that the mirror folds over too. So let's take a look at the ronchogram of one of my 30-inch thin meniscus mirrors with a single point support. And you look down at the bottom. I'm going to put my cursor there. Hopefully you can see my cursor, but at the 85% zone, somewhere close to the bottom, you'll see that there's this weird, almost like peace symbol type distortion of the ronchi bands. On the left and right, the bands don't even stay in their ronchogram channels. They are bent so far out, it's just crazy. At the top of the mirror, they're also bent out, but not quite as much. And then if you look across from the middle of the mirror, hopefully you can see my cursor. You can see how the bands fit within the channels. This one is near the outer. This one is starting to come in closer to the other side, and then this one doesn't come close. That's the sign of a mirror folding over. So it turns out that this ronchogram, the 30-inch, fits that analysis of the single point. So that gives me hope that the analyses on those other 4-meter investigations have some relevancy to what we're doing. So here's the support I have in 30-inch right now. It just turns out, luckily, that the mirror thickness and the sagitta are about the same. And I didn't bother trimming the edge of the mirror to be perpendicular. Instead, I just left it slumped. And that works out to be just a really great support for this rather stiff aluminum sling. Here's the implementation in my star test rig and my test stand rig. You can see the aluminum strap is hugging the bottom edge of the mirror. It's not quite reaching to the top edge. And then in this other picture, and I'll move my mouse over here, you can see this wood block here. This is a safety restraint block to keep the mirror from flopping out and also to keep the sling aligned on the mirror. And that works quite well at the highest power I have available to me. I also tried supporting the mirror from the hub or central position. Now, this isn't really at the center of gravity. It's actually attached to the back of the mirror. But you notice at the bottom that the wood piece that it's hung on is free to pivot and do whatever it wants, independent of the back. So there's a lot of interest in these central or hub supported mirrors. And indeed, on my old 24-inch f5.5, I had a central hub. I had the mirror cord, and I supported it that way. I also experimented with the sling. Both worked fine. This hub support also works fine. I can't see any deformation in the star test image. There are two supports that Wilson does not cover. One is the hub support I'm talking about here, being hung from the central back. The other is gluing the mirror to the supports. I briefly experimented with that by making my support points really sticky, and that seemed to be okay too, but I didn't really spend a lot of time on that. So I would like to be able to predict this edge bending business, to know what I'm up against. So here's my attempt. I ordered the mirrors that I've worked on or that I know on the left-hand side from easiest to hardest. You might, let me grab the mouse here. You might look down, here we go. So you might look down here to the lower left where my 25-inch is and the 30-inch. I would say, just based on feel and handling the mirrors, that the 30-inchers were about twice as floppy as the 25. So whatever formula I come up with better be about a 2-to-1 ratio. And this is about a 2-to-1. It better say that my 24-inch that I used to have is pretty floppy. It better say that the 20-inch that I made a long time ago is about as stiff as a 10, and the 13 was not quite as stiff, but it's still pretty stiff. So all this seems to fit in. The predictions from this model are that the 20-inch f2.5 will be somewhere in here, that the 42-inch will be out of sight. I don't know what to do about that. And then Rob Brown's, I have I guess a triplet of that mirror, you would say. A copy of that really thin 16-inch would be somewhere in here. And indeed, we heard from Rob Brown earlier that he tried a 2-point edge support and that did not work. You also notice that Dan Backen's 41-inch was glued. And I also believe David Davis's ultra thin 16 was stuck onto his support too. So where do these numbers come from? Well, it comes from the radius of the mirror to the 4th power divided by the thickness to the 3rd power. And if this turns out to be predictive, I'll try to figure out what physical meaning this has. I'm just trying to come up with numbers that make sense here. So put another way, from a graphical viewpoint, you'll see that the earlier mirrors I did don't even show up here. Then you get into those middle mirrors there where they have some edge problems. And then you can see over there, it comes through on my 25, David Davis's mirror, my 30, and then the 42-inch mirrors are out of sight. And indeed, a German amateur working on a 1-meter ultra-thin meniscus is just reporting to me a few days ago that he cannot get the sling to work. Doesn't work, even a central hub is not working. So he's going to a Schwitzinger design to see if he can get that to work. So that's rather sobering. And that edge support gremlin may be quite the beast to wrestle around. All right, so let's switch gears onto the telescope itself. One of the inspiring booklets I've ever read with telescope making is Steve Overholt's Lightweight Giants. He describes a sandwich 30-inch that fits into his subcompact car, and he drives all around California. I experimented and built several configurations of this. And what I found is that embedding the connectors into all this was a real pain. By the time I got done with that, the skin and the connectors were so strong, I just wasn't so sure what the foam was even doing. So I decided I would just go with the skin and the connectors and see what I could come up with. So here's my 30-inch f2.7 scope. And that's me holding the pieces on the left. and I am really thrilled. They are super lightweight, they are super stiff. Can't believe it, it is great. The downside is that I spend hours standing in front of the table saw, pitting out these tiny little connectors, and I'll show you some of them later. You'll also notice that I have a super low profile double flex rocker, so I can move the scope in 3 axes, and a flex base ring. The base ring actually has a Leucobond glued to the top and the bottom, and that base ring is so stiff it doesn't really flex quite as much as I was hoping it would, which is fine. But the idea of the flex base ring was that I was hoping it would kind of conform to the ground and let the scope move over it. The point of the low profile flex rockers is to get the mirror box as low to the ground to where it's almost scraping. And when the eyepiece is at the zenith, I have about a 70-inch eyepiece height. So if I stand on my toes, I can reach the eyepiece without a ladder. So I can't quite say that this is a ladderless scope, but it comes pretty close. So this is my first design where the wires do it all. I don't have adjustments on the secondary at all. It's just all with the wires. Oh, and let me grab the mouse here and direct your attention right here. I'm going to talk about this target, but here's a good picture of it. And you can also see lots of connectors around here to stiffen this up. And by the way, the whole reason that this upper tube assembly is built this way is because the wire spiders need to have spacing. So the upper end needs to be stiff. This is stiffer than my 25. I cannot deform this by squeezing this as hard as I can. This needs to be stiff so that the wires stay in place. And it needs to be stiff for the focuser. If it weren't for the wire spider and the focuser, I wouldn't need all this elaborate stiffness. And indeed, I can grab the diagonal holder frame here that the wires are attached to, and I can just move the scope around the sky just by pushing on this, and there's no change in where the collimator is pointing at the primary mirror. So this works out really well. And my table saw is very busy. Oh, I was going to say one more thing about this too. So the only adjustment I needed to really make with the wire spider after I put it together was the twist. The whole business of this twist and everything, well, let me show you in the next one here. Well, I'm going to defer that just for a minute. We'll come back to that. So counterweighting for the 3 axes. So Tom Opvos mentioned this, that if you look there on the left, you'll see the focuser and a coma corrector and a heavy eyepiece and Rob Brown's big Q-Insight finder, which is wonderful, all sitting there. And it's dragging the scope down to the left. And on a 3-axis mount, where the movements are as sensitive as mine are, the eyepiece actually begins to twist the scope downward in that 3rd axis. So I need to add about 2.5 pounds back to the right-hand side of the scope to make that work. Furthermore, that big altitude rim part of the mirror box is below the center of gravity, and that, when the scope is pointed up vertically, tends to pull the scope downward. If you look at the very bottom of my center of gravity worksheet from my Newt designer, you'll see that I calculate the total weight with all the eye pieces and everything in there is just under 100 pounds with a vertical offset of 1/2 inch. So that tells me I have a moment arm of 50 inch-pounds I need to account for. So if I do 2.5 pounds at about 18 inches above, that pretty well cancels that out. But that's also the 2.5 pounds to keep the scope from twisting on that 3rd axis. So I built a little wood box there, and I put in ankle weights. And you can see in the middle picture, you close the lid. There's a little foam in there so they don't rattle around and scare the heck out of you when you're moving the scope. So that's how I counterweight the scope in 3 axes. Right. Okay, so here's Piers helical-Crawford focuser, which is fantastic, particularly after we put the needle bearings in there. It moves so smooth. It is so nice. And you notice that I have the laser collimator and it's aimed at this target I pointed out earlier. In fact, when I first put it together, the laser dot ended up right in the center of the target. One of the big bangs of collimating for me over the many years has been trying to center the diagonal under the focuser or shimming the focuser to fit. So I finally had enough, and I remembered back a half century ago when someone who was a really experienced telescope maker came up to me and said, "Why do you have all those collimation bolts? Why don't you just build it right the first time?" And his scopes didn't have any, and they worked great. So that's always been a dream of mine. So I'm trying to build alignment into the telescope so that when I finally put it together, the collimation is just an afterthought. So here I am ensuring that the focuser is lined up properly, aimed across the upper ring. And the other part of Pierre's focuser design that I love is that there's no focuser tube barrel. Instead, it just takes advantage of the coma corrector's body and using that as the focuser tube. So that's great. And then I have an adapter and I can swap between different focusers really easily. Okay, so, well, I'm moving ahead a little bit. Let me just finish up the thought then on the wire spider. So because I don't have any adjustments in the diagonal holder itself, it turns out that it was off by about a half a degree. This is not Astrosystem's fault because they give you the adapters and screws to make that change. It meant that the holes were drilled off by a 32nd of an inch, but that actually mattered to me when I'm trying to build a scope with the wires all put together. So I had to make very slight changes, a half turn in the wire adjustment screws to rotate the diagonal all around. And when I did that, the laser was aimed right at the center of the primary. So it was really pleased. I'm really glad that the accuracy. And then when I did the final touch up with the primary, it was like 45-second collimation. Okay, so what you see in front of you are this idea I have of interchangeable bearings. So putting all Teflon pads or nylon pads is just too stiff. So I need some combination of ball bearings and pads to get the friction I want. But I wasn't sure if it would be 3 pads and 1 bearing, or 2 and 2, or 3 bearings and 1 pad. And how about if I want to put Ed Allen's system where I need all ball bearings? So I created these little cartridges. They just sit right there in position. And on that lower right picture, you can see one of them, ball bearing assembly right here, and the keeper bearings for all this. So that works out really well. And as testament to the overall scope, like I was saying, I can grab that diagonal holder with my hand and just move the scope around through that. The upper ring is stiff, the wires are stiff. The friction of the movement is nice and everything works out. So I'm pleased with that. All right, so what does the scope need next? Well, it needs a shroud to protect the silvered mirror. Oh, and the mirror needs silvering. And I need to finish designing a building, a little trolley, so I can wheel the scope in and out of the shop. The future enhancements, soon after I get it up and running, that I'd like to do, besides fixing any issues that come up, is to consider an Ed Allen-inspired clutch system. The thing is, once you use his scope, you kind of want that. It's hard to not unuse it and forget about it. It's almost as revelatory as when I first went up that first night with John Dobson's 24-inch. And I thought, oh my gosh, this is a cardboard tube. Oh my gosh, those are wood diagonal shakes or something he has in there. And oh my gosh, this is a slide focuser. What is this going to do to me? You know, will it ruin me as an amateur if I touch the scope and look through it? But it was fabulous. And the scope moves so wonderfully. And I just thought I had to have that. So it's a similar feeling when I look through Ed Allen's scope too, figure out some way to conspire to get a clutch system for fingertip movement. Also, I wouldn't mind adding a little tracking. And Jerry Oltan has come up with this, what I call equatorial table wings that you add to a base ring that turn it into a table. Or maybe I'll just go ahead and go back to my computer controlled telescope days and design a little 3-axis drive using side rollers. So here are some other 30-inchers that have inspired me as I've worked through this project. So I'm going to point you to Steve Swayze there in that second picture, because I want to talk about that scope here in a bit. And then Corman's scope, the fourth picture up there in the upper right. Boy, I've never seen a scope outfitted with so many accessories and doodads and everything you could possibly ever want. I mean, it was a wonderful scope. And I believe that scope is at Sun River now in Oregon. Okay, future projects. Well, here's my grinding machine, has served me faithfully for 3 large mirrors. And I got 2 even bigger mirrors on there, 42 inches. Not quite done with rough grinding, but almost. Sitting on top of that is a 20-inch. And then sitting on top of that is one of these ultra thin 16 inchers. It's so thin you can hardly see it. So those are my future projects. The 42 inchers will be a continuation to see how far I can push these thin menisci mirrors. The 20-inch I'm envisioning to be an enlarged zip dop that will fit the backseat of the car. The primary to diagonal distance will be 40 inches. The 16-inch will be similar with a primary to diagonal distance of 32 inches. The zip dop has a primary to secondary distance also of 32 inches. So if these are all be like zip dops, only a little bigger and fatter, the idea is to keep squeezing more and more aperture into a particular scope footprint. All right, so I want to just take a minute and editorialize here. So 13, 14 years ago, I finished the zip dop, and when I looked through it, I knew there was something new there. But thinking back and remembering, when I first went up that 16-foot ladder to Steve Swayze's 40-inch, I was convinced the scope was a failure. I'd calculated it out. I knew that I would see the airy disk of the stars. I want pinpoint stars. I don't want bloated stars. I went up there. I think it was somewhere around 700, 750 power. He was on some NGC Galaxy, and it looked like M31 in a smaller scope, and the stars were pinpoints. And you know, it was all I could do is not fall off the ladder. By the time I came down the ladder, I formulated a new idea that maybe you don't see the whole airy disk and rings because there is an intensity profile to it. And I thought, gosh, I got to have one of these too. And if I'm going to have a 40-inch, why not a 50-inch? So, you know, Steve and I, for several years afterwards, tried to come up with some 50-inch blanks. We never found someone that we could pull that off with without the blank costing what a house costs. The idea was to make 3 of those, sell one of them to finance our 2 50-inch scopes, but it wasn't a reality. And the truth is that 40-inch scope was a little bit more than a one-person scope too. Steve built that 30-inch that I showed you there in the previous picture so quickly and so smoothly and so easily that when he said, hey, I'm going to build a 40-inch, I'm sure he thought, and everyone else thought, okay, great, you know, go for it, 50-inch, 60-inch, 70-inch. But it turned out to be really more than a one-person project, that 40-inch. And it wasn't just building the scope, but it needed a giant trailer and needed something big to pull it with. Setup was a pain, you know, it's just more than a one-person scope. So at some point here, as I keep pushing up through these menisci mirror sizes, it doesn't matter if the mirror works or not, it's just going to be more than a one-person project. I'd love to try and do a 60 or 72 inch, but those are projects now. They aren't just a mirror and a scope and wheel it out in your driveway or put it in the back of your van and head out. You need leased shop space. You need a giant grinding machine. You need an observatory. You need goals and organization and money and people. And did I say money and people? And they often don't always go together so well. So now you're managing a project, not necessarily building a telescope. The project just happens to have the end goal of creating this mirror and telescope and observatory, but you're really running a project, not making a telescope. Oh, and after you finish it, then what are you going to do to maintain it? Now you've got to create another organization of people and volunteers to help run the place and keep it going. So, and I'm willing to entertain that, but I can't be a one-person, three-person project. So part of this is also bringing larger apertures down into the single-person arena. John Dobson's 24-inch is really more than a one-person scope. It really took two people to move it. It took several people to set it up. You know, it's more than one. But you look at something like Ed Allen's 24-inch, that's a one-person telescope. You know, he just even presses some buttons, puts on his shades, presses a few buttons, sits back in his chair, the scope rolls out and unfolds. It probably talks to him and does all this stuff. And then, you know, you saunter up to the eyepiece and take a look. That's a one-person scope. So we are bringing larger apertures down, but there's a limit to that, just in the nature of the scope design. Regardless of whatever limit come up across, I feel really successful. I have more ergonomic and usable telescopes with more aperture than I ever had before. Most importantly to me is I have new views of objects I've never seen before. And there are other people interested in this, which is pleasing. But I think moving from inventor to early adopter, and then next up to early majority is important. And maybe we don't build that 60 or 72 inch because it's just more than a one-person project. Maybe even the 42 inches become too much. But we're at a point now where it feels like, you know, you have this tingling sensation that maybe there's a pivot to be had here. Maybe we should look at other invention streams like digital imaging, the EV scope. Maybe there's some marriage there where we can duplicate what they do. Oh, and let's not just duplicate what they do. Let's take it the next step beyond, something that they cannot do, but something we can bring to that will take it into that new arena. So I just wanted to throw those comments out there. So there's actually another gremlin hiding. And it's these really large diagonal sizes. These are from my Newt designer. On the left shows a 42 inch that I need a 9-inch secondary. And you think, oh, a 9-inch, that's not too bad, until you realize the major axis is like 13 inches. And then you go, oh, this is a pretty big piece of glass. Even if I bend it back, like you just saw in that 40-inch, I still need a 10-inch flat. That's not an unsubstantial project. I don't happen to have a 10-inch flat. Well, if I'm going to talk like this, let's just go build a 1-meter binoscope. You know, let's just, I mean, once the burden becomes impossible, you know, doubling an impossible burden, isn't doubling infinity still infinity? This needs two 12-inch flats. What are all those weird angles up there anyhow, and all those numbers and stuff? Let me direct your attention here to the head, and let me show you how your angle tips down, because this is going to be important. So recently in Cloudy Nights, Clyde Milne, who's built several binoscopes, made an interesting suggestion. He said, if you want to get 21 ethos eyepieces into a reasonable IBD at a pupillary distance, just tilt them. And everyone's like, well, tilt them? What do you mean? That won't be looking at the same field of view. And he goes, but if you bring the axes back together to compensate, it will be the same field of view. So I understand from Cloudy Nights that Jonathan Poxton is building a 16-inch based on this design. So you see it there on the left. This is actually for a 30-inch vinyl, not a 42. But you see how the eyepieces tilt in, so you get your eyes in there. Because of that downward tilt I showed you earlier, if you look on the lower right, there's a complex geometry where the eyepieces actually rotate downward too. So it gets a little confusing. And so that's why I wrote that calculator to try to understand all those distances. So that's an interesting idea to think about too. Well, you know, I remember one time I was talking about gas mileage. Oh, I was thinking about getting a better gas mileage car. And one of my coworkers looked at me and said, "You could double your gas mileage tomorrow." And I go, "Well, how do I do that? You're not going to believe in trying to get me to believe in these fuel additives or something, are you?" And he goes, "No, just take a coworker to work in your car. Now you've doubled your car mileage." So maybe the way to double our views, double the attendu, light flux coming into our eye, is to use both eyes. So the key takeaways then, supporting the mirror's edge is quite the gremlin on these larger. It's not those other issues. And then my 30-inch, I'm trying out some new ideas that all seem to be working pretty well. And then a new idea in vinyl scopes. So that's my presentation. So thanks for your attention. And I will stop sharing and I'll entertain any questions or comments.
Thank you, Mel. That's fantastic. Your editorializing at the end was particularly interesting. Yeah, I'm really been a strong proponent of having a telescope, the largest telescope I can have, that I can easily and enjoyably set up, transport, and do whatever I want to do with it without needing anyone's assistance. And that is, I think that follows in with what you're saying about there's a limit to where that falls. It's probably different for each of us. You know, maybe for some people it's a 42-inch, maybe for some it's a 16-inch. But anyway, no, I find those comments really interesting. Dan wrote in a comment here. He said he'd like to hear more about your 3-axis tracking and Jerry's wing platform.
All right. Well, from a model viewpoint, let me back up here. So you have a couple of ways to conceptualize this. The most common way is that you have the sky in reality above you. And what you want to do is you want to model that in your computer. And then you want to find a connection or a way to adapt one to the other. So there are several well-known formula for doing that. In the software world, you know, the quaternions for the 3-axis translations and games and CAD programs are just packaged in the libraries, and it's a one-line software call now to do the 3-axis calculations. It's very confusing which way is up and down and left and right, but it is a one-line call. The other approach I've been thinking about is to consider some of this plate solving stuff. You know, a long time ago, with those giant refractors, they did not do guiding by pressing buttons and moving this multi-ton tube back and forth. What they did was they moved the image plate holder up and down the XY axis a little bit. In fact, there's quite a debate. Hubble was a huge proponent of slow guiding. He said, now just let that star oscillate back and forth, and only when you know for sure that it needs to change, go make that adjustment. So there's another way to approach this through plate solving, which is simply, hey, stop that star on the packet chip. Get it to not move. I don't need computer models. I just need to know how to get that to stop. So make the motors stop that. So that's 3 axes. Jerry's winged equatorial table. Well, Jerry, I see that you are on the call, and I bet you would like to explain this more than I would.
Well, you know, it's basically just an equatorial platform using the ground board or the ground ring as the stiff part of the structure. And then I have a little T that sits on the ground that holds the drive rollers and the idler rollers, and a little point in the back where the pin pivots on. And it turns out you really don't need a whole lot of structure for an equatorial platform. It's all there provided by the ground ring. And you can get an hour's worth of tracking out of something only 4 inches tall on a 20-inch telescope. So, you know, I found that to be a really good solution for the zip or the tridob that I bought from Mel. and for my binocular scope. Both of them sit on the same ground ring. And so they use the same tracking platform. And with a big scope that's heavy enough, you don't even have to have your center of balance perfectly matched to the platform anymore. The motor's powerful enough, it just powers it on through, whether it's balanced or not. So I didn't have to be very accurate with it. I just sort of had to get it in the ballpark, and it tracks fine.
But there is one disadvantage to Jerry's tracking platform, I'll just point out, and that is when it's tracking, and he's at high power on a ring nebula. And when someone comes up and says, hey, there's an aurora, and Jerry says, don't bother me, I'm looking through the eyepiece and enjoying the view, and other people start saying, hey, there's an aurora, and Jerry says, be quiet, I don't want to hear whatever it is you're talking about. I've got this ring nebula centered in here, and this is beautiful. I'm not touching anything. It's just staying permanently, beautifully in the field of view.
Yeah.
A few minutes later, said Jerry Olpian comes down from the ladder, looks to the north, and says, there's an aurora.
Well, first things first. I mean, how many times have you seen the central star in the ring nebula versus how many times have you seen an aurora,
Okay, so let's see, there's a couple of other comments. One from Rob.
So if I may,
I don't understand. So
I had to just type something in. I'm using my phone, and apologies for the bad spelling. But I wanted to ask about the binocular eyepieces that are angled. And as I come and look in those eyepieces, they would be diverging away from me. And
right,
so
diverging.
Yeah, what I would expect to see then is an overlap region that is not 100% of the eyepiece's field of view. Is that correct?
Yes, but you can also reorient and move the image that's coming from the other optical elements, shift them so that you can bring both fields back into merged condition.
Right, so you have a merged, you absolutely have to have a merged image. The two images are merged, but then you have kind of a central binocular region, and then outside of that, there would be monocular fields. Is that correct?
Right.
Okay.
Now here's the thing. You're thinking 80-degree, 100-degree eyepieces. Oh my gosh, 10, 20 degrees. This is terrible. No, we're only diverging the eyepieces by like 5 degrees at most.
Okay. Okay.
I'll also point out that in my 12.5-inch binocular scope, I already get that effect. The central portion of the view is binocular, and there's a little crescent on either side that I can see with one eye over here and the other eye over here. They aren't absolutely perfectly concentric circles.
So yours by tolerances, and Mel's is on purpose, by design. Probably.
Probably.
Okay. Thank you. That's good.
Okay, and then a question from Chris asking to Mel if you have thought about using the 3-inch big paracore in SIPS configuration.
No. Here's the reason. You might remember, well, no, I didn't get into that detail, so I'll just say it right here. One of the ugly things about faster than f3 scopes is eyepieces has spherical aberration. And so you get an eyepiece and you do the star test, and then you figure the mirror, and then you finally grab another eyepiece and you go, what is going on here? So the eyepieces can contribute to spherical aberration. Well, the fix for that is to alter their position with respect to the coma corrector. The coma does not really change, but the spherical aberration changes. If you, let's see, what is it? If you spiral it out, you lower the correction. Anyhow, I had to look at my notes, but you fix that. And in fact, if your mirror is smoothly corrected, you can actually fix temporary cooling down effects by altering the position too. So you can do that with the barreled coma corrector, not with the SIPs so easily.
Okay. So So are you thinking seriously about making a binoscope out of the 42s, or is this just speculation on your part at this time?
Isn't all thinking speculation, and isn't all speculation thinking?
Well, there's a difference between speculation and planning, I think.
Well, so here's the deal. I'm probably just talking, but I'm going to make both 42s at the same time. If it turns off, I can conquer this edge gremlin and actually complete these. I have a 30-inch. I don't know, maybe going for a 42 bino would be the thing. You know, the views in a 30 or something of that size, as you know, when you go up larger in size, it begins to get on most nights kind of a different view. So I'm pretty happy with the 30-inch as the largest aperture. I don't feel like I need to necessarily have a mono 42 to do that. One of the biggest problems with a giant binoscope, though, is the incredible footprint. I don't know what vehicle or trailer I'm going to buy to haul this around in. So I guess to answer your question is just talk.
Okay, for now, anyway.
Yeah.
Yeah,
But you know,
okay.
it grinds away. There's a lot of hours. You can do a lot of talk. So.
What about the 30-inch bino?
Oh, I think the second mirror is spoken for.
Ah, okay.
I spoke for it.
Oh, very cool.
Yeah.
So Mel, I'll bet you the talk changes to action if someone was to just give you a couple of, 13-inch minor axis flats that would work as a binoscope. I bet at that point you'd probably start building a binoscope, wouldn't you?
Sure. If you come over and help.
Sure, I would do
Now,
that.
you know what garage and shop help consists of, right? You get a couple, 3 beers out, you sit down in a chair, and you make comments. So.
Yeah, you can handle that.
Yeah, easily done.
Okay, we have another comment here. It's from Dan. So Dan is saying, Mel, now that you're retired, you have plenty of extra time, right?
So Howard, you're retired.
Yeah, I am.
Yeah. So how can we explain to people who are not retired what it's like to be retired? I
don't know. I don't know how to do that in a realistic way. Some people say every day's like Saturday, but that doesn't capture it at all.
Yeah, that's not yet.
No, I don't have a good way to encapsulate it. But there's certainly no extra time. That's
the thing. That's the thing. You think you can have all this extra time, and that is not the case. So, yes, I love my work, but I put in so many years at it. I'm just glad I'm doing something else. But this idea that I was going to have all this time and have all these mirrors done by now, that is not reality. That's not retirement. So, and I'm sorry for those of you who are still working, you can't get that concept, but you will someday.
That was driven home for me about 40 years ago when I started my career as a writer. As soon as I started selling stories, I quit my day job so that I would have more time to write. And I did not get any more writing done without the day job than I did with the day job. And so I'm fully expecting retirement's going to be pretty much the same way.
Yeah, Joe just wrote a comment as you do have a lot of time, but someone else gets to use it. Yeah, I think that's pretty true, especially if you're married. Yeah, thumbs up. Okay.
The list is longer, but the organization is less.
Yeah, there's that too.
Yes.
Right.
Yes.
And I've actually gotten to the point where I don't know what day of the week it is on some days. Because, if you don't have appointments or something to do, like, go see the doctor, or you got to go grocery shopping, and this, if you don't have that, for several days, you can forget what day it is.
Mhm.
So
Yeah,
that's another sign of happy retirement, I think.
I agree. Okay, a comment from Tomo wants to know, Mel, when do you plan to silver?
Aha, that depends on when Howard is willing to come over and help me.
Well, anytime.
I would like, so I've been putting it off. I'm trying to get the 30 ready to go so that when we silver it, we can go out and use it that night.
Mhm.
And
Yeah.
did I mention that retirement is not what you think it is? I just feel bogged down, you know, and can't quite get over this last hump. And it's going on and on and on, but soon.
Mhm. Well, I'm ready when you are. And just so everybody knows, I went out to observe at Mel's place with him for a couple of nights earlier this month, and got to see his beautiful new home and his incredible shop. And he's got terrific skies just right outside his door. Oh my goodness. Got to see his 30-inch in progress, as he showed the pictures of earlier. And we were sitting around talking, and then the second night turned out to be cloudy, and we talked some more. And we're talking about silvering, and I asked Mel, well, how much does those 30-inch mirrors weigh? And you said, what was it, 35 pounds?
38
34?
pounds each.
38 pounds each. And I'm going, 38 pounds. Man, that's pretty easy to pick up. It's a lot lighter than the 92-pound 28-inch mirror I have. And then funny things started to happen in my brain. And after a few moments, it's like, well, there's an obvious solution to Mel's extra 30-inch mirror. So we made a deal. And so my 28-inch is going to transform into a 30-inch telescope because there's room in the mirror box for a 30-inch mirror. And now when I need to resilver it, instead of writing my will before doing so, in the off chance I actually break my back picking up a 92-pound chunk of glass, this 38-pound chunk of glass is going to be so much easier to lift, and this is going to extend the amount of time I'll be able to use my big scope. So anyway, long story short, I'm pretty excited about this opportunity, and I'm hoping that when I'm 80 years old, I'm still able to put my telescope into the back of my van and drive off somewhere really dark and set it up by myself and have a great time. So, and if I am, thank you, Mel Bartels, because there's no way I know I could do that with the 92-pound mirror I have now. So, there's another comment here about retirement. Once from Kathy and Tim. It says, once retired, you wonder how you ever had time to work. That's, yeah, true enough. All right, so any other comments? I took too much time with my little story there. But if not, we'll hand over the floor to Dan for the final presentation of this year's workshop about the update on the 36-inch f4 direct drive telescope.
I hope this works. Can everybody see this?
Yes.
Oh, good. Can you see my mouse?
Yes.
Okay, we're off to a good start.
Yeah. Okay.
Except I pressed the space bar and it didn't go to the next screen. Okay, there we are. All right, so I just had to look up on the Wikipedia, how much does it cost for a year of going to college? And it's about $10,000 a year for a public, and it's about $33,000 for a private a year. And I was thinking, well, I'm still going to school. And I am. And in building Jimmy Scope, I learned a lot, some of it the hard way. And so this is going to tell you about some of those learning experiences. So this is the original design, and it's pretty close to this. You probably might remember this from last year. And what you'll notice here is we have 2 altitude motors and 1 on each side. And my thinking was, oh, can everybody hear me okay?
Yes, yeah, you're coming through just fine, Dan.
Okay. And my thinking was, well, we can apply the same exact torque to both sides, so it's going to eliminate any twisting. And it turns out that even though that worked in that respect, I had so many harmonic resonant frequencies on this mount, I had to give up that design. I'll show you a little later what we did instead. And this is a pre vaccine time. That's Daniel. And this is a scope as it sits now. And you can see the motor is here on the altitude motor. And you can see Daniel up there working on the secondary cage, I think. And here it is, so you can have a better resolution view of it. And so he's wearing a mask. We all wore masks while we worked here until we were all fully vaccinated. And it's nice to have that. We don't have to wear masks anymore. Okay, one thing that came out of the workshop last year, and it was Richard Berry that kind of pressed me on this, and I was just going to try to mount that encoder ring that you can see where my mouse is right here. That's the absolute encoder ring, and how to center it. And he said you should make that adjustable with some kind of a sleeve or something. And then I got Ed Harvey involved, who is kind of the creator of the Flex Rocker a couple decades ago. Anyway, and he works at our company TMS. Well, if you can see this, it's really unique. I just love this. This is 3D parts, and Taj, who's here listening, he works here, and he helped me print these 3D parts. And we put in brass inserts, and let's suppose that we put a dial indicator on this, and we have to move the encoder the way that my mouse is moving. So what you do is you loosen this just a little bit so it can slide. You loosen this one just a little bit so it can slide, and then you loosen this. Say you win a certain amount of thousandths, then you know the pitch of the screw. So you turn this screw that exact amount, and you turn this screw that exact amount, and then you tighten this one, and then you snug these two up, and then you test it again, and it's right. It's like perfect. So this is the slewing bearing, and it's a really rock solid bearing, and it holds a lot of weight. And we built a motor. You can kind of see the motor. I'll show you more parts of it. It has 2 layers of magnets and 2 layers of coils. And we'll take a look at it right now. So what you're seeing here is the rotor of the slewing bearing, the part that moves. You can see right here is the encoder. And then you can see 2 layers of magnets. And then in the same, just outside the magnets, are these coils. I forget now how many. I think there's 32 magnets and 24 coils. I'm pretty sure that's right. And then there's a ball bearing that keeps it centered. And here's both together, a kind of a zoomed in view. That's the heart of the azimuth. So this is the azimuth without the bearing, but it has the aluminum plate, and it has the bottom row of coils on it. And what I want to point out is these 4 plates that it rests on, and there's nothing underneath this aluminum disc. It's just resting right on those. And we had our first major problem was the azimuth had a lot of friction, way more than the manufacturer said it would, as far as friction, like 4 times as much. And the motors weren't powerful enough for that. And it would have taken too much energy anyway to push it. So, you know, we were in contact with them and they had some suggestions. But one day we were testing it and we had it on a workbench, that big slewing bearing. And we found out that when we clamped it to the bearing, it got hard. And when it was not clamped, it, even though it's a massive bearing, it does flex and it does get tight. So the solution is what you see where my mouse is. And we water jet cut a steel ring and we welded that to these 4 pads. And then we took this to a machine shop that had a big enough lathe to face it off, and it completely solved the azimuth problem. And so then we started proceeding with the altitude, getting that to work right. But in this picture, you can kind of see the whole thing. You can see the encoder ring is not here, but here's the amount for the encoder itself. So this part here is stationary, this part here turns. And here's another view of the, oh, this is the top one where it holds the reed head bracket. And then here is that same thing that's welded. And this is another picture of the bearing, that the big slewing bearing. Okay, so let's see, I went to the too far. Okay, so this is to show you the, whoops, the altitude motors. And you can see that they were originally designed, we had a segment for the coils, and I think there was 9 coils. And then we used a larger segment for the magnets. And I thought this was going to work perfect. And we had so many resonances. Oh, here's the reed head, and that worked well. We're still going to use that. And then here's the parts for the altitude bearing. And we've taken the magnets off because they're very dangerous. If you've ever worked with magnets, those magnets are so powerful you can break fingers and things. So here's a segment of the coils, and here's the segment or the arc where the magnets go. And so one of the guys that used to work here, he's employed elsewhere now, Joel, kind of invented this design that, and Taj again helped me print this, but this part here has a ring that sets right up against this radius, and you just put it on there and put the first magnet in, screw it down, put the second and the third in, and then after that you move this thing, and so that this point here goes over the third magnet you just did, and you do 2 more, and then you do 2 more, and it's so safe and it works so well. So if you're ever doing that, that's a really good idea. Okay, so we went from this to this. So you can see this drive disc, you can see the 2 motors here, and now you can see the drive disc here, and there's a drive roller here and a reducer. I'll show you more detailed pictures of that soon. And this is the stainless steel drive disc that we had water jet cut. And it is a certain stainless steel. I wrote it down and I can't remember what it is right now, but we'll see it in a slide or two. This is the roller. And if you can kind of see right here, there's a radius on here. So the radius contacts the surface of the drive disc. And tomorrow morning, I found on Facebook, the marketplace, somebody selling this kiln not too far away from here. So tomorrow morning, I'm picking it up and we're going to harden this piece so that it's hard. It'll be harder than the stainless steel, but it's going to be the one that's the toughest. Okay. This is a reducer. It's not a harmonic drive, but I believe it's exactly the same principle. There's no backlash in it. And this is a 16-to-1. And we made this piece that I showed you in the previous slide. We made that on our CNC lathe so we could do the radius. And then Oh, I made an animation. I forgot. Just for fun. So you can see the whole thing. And then this is the brand is Onvio, and it's really rock solid. It's very, very powerful for even sideways motion, which we need a lot of. Okay, and then I wanted to talk a little bit about the hardness of the steel. Successful roller drives pretty much need hard steel on steel. And so using the Brunel units, I guess, I don't know that much about it. Regular steel that you would, get a piece of flat bar or angle iron. It's Brunel's 126. That drive disc is 17.4. That's the name of it. It's like I've heard of 316 and all the other things, but 17.4 I hadn't heard of. But Daniel, who works here, found that that's a pretty hard stainless steel. So we found a place locally that was able to provide that and water jet it. And then we machined it in our CNC milling machine. We had to machine two parts to it. The 3-inch hole for the axis, we had to machine that. And then we also machined the radius for the turning radius that the roller drives on. So those were machined, and they turned out real nice. And the tool steel with that new kiln that we have, we should get to about 650 hardness, Brunel hardness. So here's a look at it. Here's the brushless motor right here. This is a pivot point right here. And this is another bolt where you can push this up or down slightly and keep it tight. And then this is a bolt, and these are are spring washers. So any deviations in this roller thing, the spring washers will take it up. And it works really well. Here's the inside. You have to imagine the belt. I didn't draw the belt. And here it is installed. I think that if I click here, we'll have a movie. Let's see. Yeah. Okay, that's my Studebaker. Some of you have seen that Studebaker. There's a Cal Poly scope. And then here's the telescope. And you can see it's moving. Now,
And I'm not seeing the video.
what's that?
I'm not seeing your video. I'm just seeing the still picture of the altitude drive.
Oh.
You have to reshare you have to share the video screen.
Oh, yeah. Okay. So I'll stop this share because it's worth doing. And then share screen. Okay. I'll start it over. Can you see it
Okay.
now?
Yeah, we see it.
Okay, sorry about that. You probably didn't see the previous animation either. That's all right. Okay, so that was a Cal Poly that drifted by. Some of you know about that. And then and it solved all the problems, and it's stiff, it's fast enough, and it's because of the encoder on the opposite end, it's really accurate because of the Renishaw encoder. And it works well. So I'll show you the next. I'm going to show you the other side of it. So that's the reducer, 16:1 reducer. And then if we go inside, you can see the motor working. A little bit out of focus, but that is solved all our problems. So we really have no showstoppers anymore, and we're back on track. So this is the encoder, the Renishaw absolute encoder. And I have one more thing to show you. I think I'll jump ahead just a little bit. Okay. So this is the software, and I'm running a script, and I just stopped it because I wanted to show you what it's doing tracking now. So now it's tracking, and I hope we can see it. Okay, there we are. I'm going to pause it. Okay, so I wanted to show you this S-axis error. That's the secondary axis error. So in this case, it's the altitude. I haven't even tuned the primary axis. That's just a motor sitting up. You'll see it. But it tracks so well. This is based on that absolute encoder. And we're like 0.1 arc seconds RMS tracking. I mean, real tracking. And then you can see the primary axis has a little bit more error. You'll see it. There's the primary axis. Let's see. Oh, I guess I didn't give you a very good. Oh, there we are. See, we just needed to have a motor on the since it's not on the azimuth right now. We needed on that big motor that we made and everything. We just needed a way to test the altitude. And so this has not been hardened yet. We have to make a new one out of tool steel, and then we'll harden that, and then this will be done. And okay, so that's it. So now I guess I have to reshare my screen. And, I hope this is the right one. Oh, no, here it is. Okay. Whoops. I got the movie up again. How did that happen? Okay. Okay, so now I'm going to talk about what's left to do. Jimmy is waiting patiently. Thank goodness he's been very patient. This has taken a lot longer than we thought. And I'm leaving out a lot of details, but we have to completely reassemble, which we should get done next week. We'll put that big the azimuth motor and the bearing, everything all together, and put the fork on it, and then make sure everything is tuned and working really well. And then depending on the weather, we could put the mirrors in, but I'm kind of skeptical of the weather. We have to work on the leveling system because it rolls out of a trailer, and then you set it up with the leveling system. And then the fans and mirror covers, and we have to make a tip over mechanism so that one person can put the secondary cage on. And then we have to disassemble it all again and paint everything and anodize everything. So we still have a ways to go. And there's probably a lot of other details I'm leaving out there. And this is the weather in this time of year. So, you know, we might get something. I think that's all of my my presentation, yes. So let's see if we got any text. Any questions or texts?
I have a comment, and wow. Yeah, I know you've had some surprises along the way, but that new altitude drive is really slick.
It is. It really is.
The one thing I don't understand about it is that the roller that the sector is riding on, it's riding on the curved section. What is that the part that's sticking out another few inches?
Oh, it doesn't need to be that long. I can make it shorter.
Oh, okay.
Yeah.
All right.
I
couldn't figure out what it was for.
Well, yeah, I know why. It's because the reason I made it that long is because that reducer had something on there that was that long. I didn't want to cut it off. Yeah.
Okay. And so the screen you showed us on its tracking, you said it was 1/10 of an arc second accuracy.
Yes, that's it, like the jitter and stuff that on the tracking jitter. Yeah.
Wow.
Yeah, I mean, I'd imagine that the pointing model on this telescope is probably going to be, I mean, if we did a photo model, I mean, I'm not sure we will, but if we did a photo model, it would probably be in the 4 arc second RMS range. And I speak from experience, and that's really because of Dave Rowe's software, the Point XP.
Sure. Oh, my goodness. I mean, that to me, that just sounds exceptionally good for any telescope, let alone one this size.
Yeah, well, you know, the way that Jimmy observes is he uses a computer to pick his galaxies. He's a galaxy guy, and he goes, he wants it to be there. He wants it to track well. He doesn't want to mess with finding things. he wants to see all of the galaxies that he possibly can.
Oh yeah, this will
Yeah.
certainly do it for him.
Yes.
So I'll venture a guess that after he's used this 36-inch for a while, he's going to ask you to come down to his place in West Texas and make his 48-inch the same way.
Yeah, well, yeah, I'll have to ask my wife if she'll let me.
You might not come home for a while. Yeah. Holy
Yeah.
cow. Okay.
Well, it's been a learning process and still learning. So that's
Okay.
why, yeah. So any other questions?
Yeah, Dan, how much is it going to weigh?
It's going to weigh like about 14 or 1,500 pounds. You won't be picking it up.
No. Okay, we had a couple of comments here on chat. One is kind of side questions is, where is the Cal Poly scope these days?
Well, did you see that in the movie?
It's right there.
Yeah, I walked out from where I'm sitting right now. I have the mirrors resilvered, and they're good mirrors, it turns out. We found that the secondary was mounted, it was creating stress in the secondary. So we got that fixed, and we did a lot of testing, and it really, really works well with the rotator and the focuser and all. And we measured at my observatory. I kind of loaned my 12.5-inch CDK, plane wave CDK. I loaned that to Russ Janae. So he's got that. He's trying to get his telescope working down there in Arizona. And there's just enough room in my observatory. If I slide the Altaz mount away for this thing to swing down, I mean, it'll have to be looking at the azimuth so you can close the roof, but it just fits. So it's going to go there when I get some more time.
Yeah,
I guess I have to retire first.
You have to retire to get to be even busier. Yeah. Okay, then Chris wrote in. He says to thank you. He says he will now redesign his 2-motor altitude system to find out now harmonics will not let it work.
Well, I would answer that if you can hear me. Are you online? Yeah, Christopher Tribe. Yes. I think we should give it a chance. It might work really well. You don't have such a long poles, and it might work a lot better than you think. So when you can get it over here and test, I mean, I think you have it all made, right?
I do. I have it all made, and it's very similar to what you have done, but I think I'm probably going to run into the same harmonic problems.
I'm not so sure. I'm not convinced. I think we should try it. It won't take but a couple of hours to get it hooked up and try it.
Okay.
So if you can get it out here, I'll find the Force One around and we'll hook it up and try it.
Sounds like a good winter project.
Yeah.
In a few months.
Yes.
Thank you.
Chris and Dan, when you do that, let me know if you don't mind somebody looking over your shoulder.
I don't. Who is talking?
This is Greg.
Oh,
Jones.
Greg Jones. Yes. Okay. I'll see you next week, I guess.
Yep.
Yeah. Yeah. That we'll do that.
Hi, Dan.
Sounds good to me too. I'm more than happy to get any help I can get.
Do you have okay.
Go ahead, Tong.
The altitude drive, do we have the 2-stage reduction? The first stage is about?
No, on the azimuth, it's direct drive. Oh, yes, on the altitude, yes. There's a timing belt. Yes.
Timing belt, right?
Yes.
Okay. Do you have no backlash with the timing belt? Does that work well?
No, very little backlash, and plus, it has it's an 18-inch radius on the drive disc, and it's about 1.4 inches in diameter of the drive roller, and then it's a 16-to-1 harmonic drive, similar to harmonic drive, and then I think it's about a 4-to-1 on the timing belt.
Okay,
And so by the time you get to the timing belt, any inaccuracies in the timing belt will be pretty minimal. And
sure.
also the encoder on the other side of the OTA
Yeah.
takes out anything. So
So you use absolute encoder, not not the relative, right?
yeah, these are absolute encoders. Yes.
So what is the benefit instead of just
What is the what?
what's the main benefit of the absolute encoder for the compared to the relative?
What is the accuracy?
I mean the absolute encoder. So what's the reason to use the absolute encoder?
Oh yeah. Well, by the time you have incremental encoders, then you might as well have absolute encoders. And you turn the power on, it wakes up, it knows where it is, and the resolution is really good. It's
Okay.
It's 2 to the 20. Well, actually, these are 32-bit encoders, so 2 to the 32, 2 to the 32nd. That's like 2 billion ticks, but that's way oversampled, so we don't use all those bits.
Okay.
Yeah, we use 26 of them, which is about I think there's about 51 ticks for every arc second.
Okay, thank you.
Wow.
Hey, Dan, what's your power consumption estimates, especially with that azimuth drive?
Well, the nice thing about it is horsepower is torque times the RPM, and there's no RPM, it's just torque. So torque is done by the current, but you're chopping the current. So say you have 3 or 4 amps going through the motor, you don't have 3 or 4 amps coming from the battery. So I don't know exactly yet, but it's probably about, I think we had about 4 or 5 amps on the motor. The altitude motor doesn't take much at all. The azimuth is going to take a little bit more to get the torque.
So is this 12 volt or 18 volt or
No,
what?
we're going to go with, we're hoping for 24, but we might have to use 36.
Ah.
And that would be for the azimuth motor.
Okay. Wow. Can't wait to see this thing in action.
Yeah.
It's going to be really, really pretty incredible.
Yeah, me neither.
Yeah, I'll bet. I'm sure at this point you're ready to be finished.
Yeah, and we lost one of our workers. I mentioned it earlier. Joel found another job, so so we lost Joel, and he was doing a lot of this. So mainly it's Daniel and me doing he does most of the work. So I just help when needed. So, and Taj does too. Taj is here listening in. So I'll see you.
Hi, Taj.
I'll see you Monday, Taj.
Hi, Dan. Since this is supposed to be, I guess, semi-portable, what are you going to do to offload it from the trailer, I guess, or semi, or whatever you're going to use to move it with?
Well, Jimmy told me the dimensions of the trailer, and it fits in there nicely. And we're going to have a couple of ramps. They got to be pretty strong ramps, and it rolls really nice. It just rolls just on the concrete floor. It just yeah.
Hi, Taj.
Go ahead, Tom.
I just say hi to Taj.
What, Tom?
Oh, I just say hello to Taj.
Oh, he said, yeah. Taj and Tong have spent a lot of time together on the phone and stuff. So yes.
Thank you for all the help, all the trouble I give to you.
So Dan, I noticed the altitude bearings, they don't look like they encompass a full 90 degrees. Is this scope just designed to not go all the way down to the horizon, or am I missing something?
Oh, no, it'll do the full 90. It's more than 90.
Is it really? It didn't look like those bearings were 90 degrees out.
Are you talking about the drive disc?
Yeah.
No, it's a I can't remember, but it's like 110, I think.
Okay, it just didn't look like it to me.
Yeah, right. Yeah, it doesn't. You're right, it doesn't, but it is. Yeah.
Okay, interesting. All right. So, any other comments or questions? I can imagine Ed's wondering or thinking that you're missing a beat by not putting tractor treads on this thing.
Yeah.
I'm just thinking 1,200, 1,500 pounds down a ramp.
Well, we're gonna.
I don't even like to move 200 pounds down a ramp.
Yeah, well, it's gonna have to have probably a winch for that. Yes.
Yeah. Okay.
Okay, great. That's a great.
Okay, so sounds like this is it for this year's workshop. Last year at this point we were talking about, boy, it sure be great to meet in person again and a TMS workshop and get back to like we used to do it. That didn't work out this time. Hopefully next year, 2022, we'll be able to do that again and incorporate some of the Zoom technology we've become accustomed to, so people from around the world can present and attend as well. That'll be an interesting challenge to do a hybrid live and Zoom event, but I'm sure we'll be able to figure that out. The thing I'd like to get some feedback on, either now or you can think about it and send me an email, is how the Zoom format has worked on your ends. Has this been a viable option for the last 2 years? Do you think it would be good to continue? Maybe this is better for some people rather than being in person in a workshop. I don't know. So I'm curious about just, whatever your thoughts are on how we have the workshop going forward. I'm hoping to get back together in person, but maybe that's not true for everyone else. So give us some thought. If you have any thoughts off the top of your head right now, I'd be interested in hearing them as well. But if not, just send me a note, and we have a whole year to think about it. We'll take it from there.
I really, really think we should do both, heavily both, because I too would really like to get together, and it's a lot of fun, but it opens it up to people all over the world,
Yeah, it does, and I think that's a huge benefit. So when we do get back together, incorporating Zoom as part of it is, I think, going to be important. I'm not quite sure how that's going to work. It's going to take more of a production to do, because someone is going to have to be in charge of making sure that they're capturing on the Zoom video what's happening in the presentation in person, and making sure that they're getting good video of whatever telescope or device is being talked about. But anyway, that's something we can figure out, hopefully. And also, I'm curious what everyone thinks about holding it this time of year. We've had it in October for the last 2 years, and previously we've had it in late July and early August. So give that some thought too. It seems to work well in terms of having it in October, in that fall weather has come in. We don't have a lot of clear nights that we're giving away. Of course, we're doing it around full moon as well. But anyway, give all that a thought. And if you have something you'd like to share, just pass it on, and we'll take it into consideration for next year. And okay, so with that, I think we're finished.
Oh, you had beer? Okay.
Dan's got his beer.
There you
Yeah,
go.
that's
Dan.
not a bad
Cheers,
idea.
everybody.
That's not a bad idea.
Cheers.
I think I want to go grab a beer.
Yeah,
So-
thanks. Yeah, I'm just about out
I
of
will.
tea, so it's beer time for me too.
Okay.
So I'm going to stop the live stream now. I won't
Okay.
stop the.
Good job, Howard.
Thank you.
Okay, thank you, Howard.
Thank you, Howard.
Thank
Very
you,
good
Dan.
job.
Thank you
Thanks
very
for
much.
hosting.
It's a lot of fun. This is totally
Okay.
worth it.
Yeah.
So I'm going to stop the live stream and the recordings, but I'm not going to stop the workshop because